Let's look at the potential, the electric potential of a point charge. So we know that the potential energy is between two charges. We can only have potential energy if they're interacting objects. We know that if we have some charge Q1 and some charge Q2, that they will have a potential energy that looks like 1 over 4 pi epsilon naught, the product of the charges divided by the distance between the charges. But say, for example, we want to know about the potential, which is just how much energy is there per charge. We would ask, what is the potential that is produced by, let's say, charge 1, and then for any amount of charge 2, we know that if we multiply that potential by whatever charge 2 is, that will give us the potential energy. So it's sort of like asking how much energy could an electric field provide to some unknown amount of charge. And so we define this quantity as the potential energy per charge, where Q2 is the charge that we are curious about how it might be affected by charge 1. And so this would then look like 1 over 4 pi epsilon naught Q1 over R, where R is just some distance away from that charge Q1. And so we can think of a situation where we have some negative charge. Let's say that Q1 is equal to negative 1 nanocoulomb. And we know that the electric field for a point charge like this points inward because it's a negative charge. And we know that the electric field around that point charge is going to be constant at any particular radius away from that point charge. And those points along those spheres where the electric field is constant are the points where the potential is also constant. And so that means that there is an energy difference between any of those places. If we go from one constant electric field point to some different constant electric field point, that's a change in the potential, which means that if we were to place a charge at one of those constant potential spheres, the equipotential, that there's an energy difference between it and some other constant potential or equipotential surface, like one of the other sphere. And so we could say, well, what if we put a point here, and this is 1 meter, and say we put another point down here, and this is √2 meters. So it's as if this forms a right triangle where the two sides are 1 meter long, and then the hypotenuse here is square root of 2. And so then we ask the question, what is the potential difference? And we're almost always interested in a potential difference, a delta V, because that's a change in energy that would occur going from one particular place in space to another. So I'm going to call this one R2 and this one R1. And then I'm going to calculate the potential difference. And since the potential is a constant times Q1, another constant, times 1 divided by R, I can pull all those constants out and just say that this is 1 over R1 or I'm sorry, 1 over R2 minus 1 over R1. And I know that this is 9 times 10 to the 9. I've chosen 1 nanocoulomb. And my distances are 1 over root 2 minus 1 over 1. And when I calculate that, my delta V is 2.64 times 10 to the 0, so that's 2.64 volts. Or I could say that V2 is equal to 1 over 4 pi epsilon naught times minus 1 times 10 to the minus 9 coulomb times 1 over root 2 meters, which is 6.36 volts. And I could calculate V1 as well. And that would just be 9 volts. And so I would have, and sorry, this is negative in both cases because of the negative charge. And so I would have V2 minus V1, which is delta V, is equal to minus 6.36 minus negative 9. And when I calculate that, I'm going to have a negative plus a larger number, so that would be a positive 2.64 volts. And we can check our answer by using this PhET simulator that looks at the electric fields. And we can see if we place a 1 nanocoulomb charge in the middle of the screen here, the grid is, each large block is half a meter. And so I can take this voltmeter and I can put it 2 blocks away. And obviously this is an estimate, but we can see that that's at about negative 9 at that point. And I can click the pencil to draw that equipotential line. It's a circle like we said before. And then I can come down here diagonally 2 blocks so that I'm at square root of 2. And we see that we get 6.359 volts negative. All of these are negative because it's a negative charge. You can draw that equipotential line, and if I take that difference, I'll get the value that we saw in the example calculation.